Hello students, welcome to Saurav Sir's classes. Today we are going to solve few numericals based on ISI subjective part. In ISI question paper we have two parts, one subjective and the other one is objective, which is MCQ. So here we are going to discuss about the subjective parts. So let us begin with our very first sum. So our first sum here says it has two parts, part A and B. So part A is A be a n cross n orthogonal matrix. Okay, so we have been given a matrix A, which is n cross n matrix and also an orthogonal matrix. So what do we know about an orthogonal matrix? An orthogonal matrix represents that this is part A. Orthogonal matrix says that A dash will be 1 by A. So this is basically A prime. So this is also this can be represented as 1 by A because A is orthogonal. Now with respect to this equation, we can assume any character, we can assume any letter, say let K. Let this be the characteristic root of A, characteristic root of the matrix A. So let K be the root of A. Since K we have assumed to be the characteristic root of A, then we can represent K in this form. So here we will have K equal to 1 by K. Now solving this further, taking K this side, we will get K square equal to 1, and rooting both sides we will get K is equal to plus minus 1. As you know, rooting of any numerical will give us plus minus 2 signs. Possibility is plus or minus. So here we have K equal to plus minus A. Now in the question, let's proceed what we have been said in the question now. When n is even and suppose det A is equal to minus 1, where det A denotes the determinant of A, show that I, which is an identity matrix, minus A, and determinant of that is equal to 0, where I denotes the n cross n identity matrix. Okay, so now we have been given another condition where det of A, determinant of A is given to be minus 1, and we need to prove that det of identity matrix I minus A is equal to 0. So this we have been given, this we need to prove. So let us first write down here. Here we have been given that det of A is equal to minus 1. So seeing this, that det of A is equal to minus 1, we can simply say that this implies that there is at least one K of I which must be a 1. We have assumed that we have a matrix here, where here we have K of I j, K of, yeah, so each of the element is K of ij, where I belongs to 0 to I belongs to 1 to 4, whereas j also belongs to 1 to 4. So basically this is the matrix. Let us assume this matrix, and it is 2 cross 2 matrix because we have been said in the question that n is an even, which can be, we have assumed here to be 2. So this is n cross n matrix. Now in this, when we det of this matrix, that is Kij, we have 4 terms. So when we det of this matrix, we are getting a value which is minus 1. So this implies that we have any one of these values to be equal to 1. We must have any one of these 4 values, or it may be 2 also. Any 2 or any one value should be equal to 1. So from this we can say that K is equal to 1. Any value K is equal to 1. So here we have got a value to K which can be 1, and here you can see it can be minus 1 also, but this states that K has a value which is equal to 1. So in this equation, what we needed to find, here we have identity matrix A, identity matrix I minus A, and that of that is equal to 0. So let us write that here. Here we will have identity matrix I minus A. So here you can see identity matrix means 1 into identity matrix minus, here we can see that K is equal to 1. Therefore we will have that our matrix A is also a representative of an identity matrix. So this can also be written as 1 into identity matrix, because here we have a value 1 and the total value is minus 1. So here we can have an identity matrix, or this can be put in an identity matrix form. So we can write this as I of A, therefore 1 of I, which gives us a value equal to 0. So this is what we needed to prove. This has come up because k is equal to 1. We have the condition k equal to 1, therefore we have this equal to 0. This is what we needed to prove in part A. So let's proceed to part B. So here we have part B, which says let A and B be two n cross n real matrices such that A square equal to A and B square equal to B. Okay, so in A we had only a matrix A, and in B we have two real matrices, same n cross n real matrices, and we have the matrices A and B, and the condition is that A square is also equal to A and B square is also equal to B. So suppose that I minus A plus B is invertible. Show that rank of A is equal to rank of B. Okay, so here we have been given that I minus A plus B is an invertible matrix. So here we can write this as I minus A minus B, and this matrix is also an invertible matrix. So here we can multiply this matrix with A and B respectively. So let's multiply here and let's check whether their equations can be same or not. So here we have I minus A minus B. So let's open the brackets. We will have AI minus A square minus AB. So as you know, any matrix multiplied with an identity matrix gives the matrix itself. So here we will have A minus, we have A square. So in question you can see A square is equal to A. So we can write this here A and minus AB. So A minus A gets cancelled out. We are left with minus AB. Similarly, we will multiply this with B, but we will multiply the matrix first and then we will place the B. So since this is invertible, we can write this as I minus A minus B into B. So here it will have I B minus A B minus B square. So IB, again any matrix multiplied to an identity matrix gives the matrix itself. So here we will have AB minus AB minus B square. So in question you can see B square is equal to B. So we'll write here B. So BB gets cancelled out. We are left with minus AB. So as you can see, we have both sides minus AB minus AB. So the rank of minus AB is equal to obviously the rank of minus AB. Hence the rank of this will also be equal to the rank of this. So let me write this here. We can write that rank of A will be equal to the rank of this. That is why I have multiplied A with the in the beginning. So here we can write rank of A will be equal to rank of total A into I minus A minus B. So this is a rank of A equal to rank of this, because both of the matrices will be of same number of the dimensions will be same, which is n cross n. Therefore the rank of both will be same, because we are multiplying A with this and we are equating this to the rank of A only. So this can be said as rank of minus AB, because this is obviously the simplified form of the statement. Here we can see minus AB is just the simplified form of this statement. Therefore the rank will be same. So this can also be written as rank of, here we will have I minus A minus B into B, because here also you can see minus AB is the simplified form of this equation. So both the ranks will be same, and from this we can say that this is equal to rank of B, because here also we have n cross n matrix, here also we have n cross n matrix, whereas here we are multiplying this single matrix with another matrix B, and here we have only the matrix B. Therefore both the ranks can be same, both the ranks will be same. So from here you can see rank of A is equal to rank of B. So this is the required equation. Therefore rank of A is equal to rank of B. So this is what we needed to prove in the question. As you can see here, we have rank of A is equal to rank of B, hence proved. So here is the end of our first question. We will continue with the other questions in our further videos.